Global Navigation Satellite Systems, GNSS, are invisible pieces of technology that people rely on every day without thinking about it. From communications systems to mobile navigation applications like Google Maps, GNSS affects what we do every day. But what are global navigation satellite systems? A global navigation satellite system, GNSS, is a network of satellites broadcasting timing and orbital information used for navigation and positioning measurements. GNSS are more than the satellites orbiting Earth. The multiple groups of satellites, known as constellations, broadcast signals to master control stations and users of GNSS across the planet. These three segments, space, control, and user, are all considered part of GNSS. But most frequently, GNSS is used to describe the satellites in space. The space segment describes the GNSS constellations orbiting between 20,000 to 37,000 kilometers above the Earth. These satellites broadcast signals that identify which satellite is transmitting and its time, orbit, and status or health. There are four main constellations in orbit: GPS, GLONASS, Galileo, and BeiDou, as well as two regional systems QZSS and IRNS, and each are managed by a different country. The control segment is a network of master control, data uploading, and monitoring stations located around the world. These stations receive a satellite signal and compare where the satellite says it is with orbit models showing where it should be. Operators at these stations can control the satellite's position to correct or alter their orbital paths, for example if a satellite has drifted, or needs to be moved to avoid debris collision. This process, as well as monitoring a satellite's health, ensures a baseline of accuracy in GNSS positioning. The user segment includes the equipment that receives satellite signals and outputs a position based on the time and orbital location of at least 4 satellites. This segment includes the user's antennas to identify and receive good quality signals, as well as high-precision receivers and positioning engines that process the signals and resolve potential timing errors. The basis of GNSS and its technologies is in using radio waves for communication and tracking a position. These efforts were applied to space when the Soviet Union launched Sputnik 1 into a low orbit in 1957. Sputnik, Earth's first artificial satellite, transmitted radio pulses for scientists to learn about the density of our atmosphere and to test radio and optical methods of orbital tracking. Due to the political climate, it also sparked the space race between the USSR and USA. American scientists tracked Sputnik's radio pulses using the Doppler effect, a method that eventually led to the Navy Navigation Satellite System, also known as transit. A global navigation satellite system, GNSS, is the generic term for any of the satellite constellations that broadcast positioning, navigation and timing data. There are 4 main constellations and 2 regional constellations worth highlighting. These constellations use radio frequencies in the L-band to transmit their signals, however each constellation may choose different frequencies and corresponding labels for these signals. GNSS positioning equipment typically receives at least 2 frequencies, which more specialty equipment able to receive additional L-band signals. Important to note are satellite-based augmentation systems, SBAS, which provide global error corrections for improved accuracy in GNSS applications. Many countries manage their own SBAS systems, and these are usually considered separate from traditional GNSS constellations. GPS is operated by the U.S. Space Force, a branch of the U.S. Armed Forces. It was the first constellation to be established in space, with its first satellite being launched in 1978, with its first series of satellites fully operational by 1993. Currently the system has 31 satellites in orbit supporting L1, 1575.42 MHz, L2, 1227.60 MHz, and L5, 1176.45 MHz, frequencies. GLONASS was first developed in the Soviet Union to compete with GPS during the 70s and is currently operated by Roscosmos State Corporation for Space Activities, a department in the Russian government. The first GLONASS satellite was launched in 1982 and today has 24 satellites in orbit. The constellation was fully launched and completed in 1995, with full satellite coverage achieved across Russia in 2010. GLONASS satellites broadcast signals on GLONASS L1, 1598.0625 to 1605.375 MHz, L2, 1242.9375 to 1248.625 MHz, and L3, 1202.025 MHz, frequencies. Galileo is a more recent constellation first launched in 2011. Operated out of the European Union by the European Global Navigation Satellite Systems Agency, Galileo currently has 26 satellites in orbit, with a plan to reach 30 satellites by 2021. These satellites transmit along the L-band spectrum, labeling their frequencies E1, 1575.42 MHz, E5, 1191.795 MHz, E5A, 1176.45 MHz, E5B, 1207.14 MHz, and E6, 1278.75 MHz. First launched in 2000, BeiDou operates out of China by the China National Space Administration, CNSA. In the 20 years since, BeiDou has 48 satellites in orbit. BeiDou satellites currently transmit many signals, including B1I, 1561.098 MHz, B1C, 1575.42 MHz, B2A, 1175.42 MHz, B2I and B2B, 1207.14 MHz, and B3I, 1268.52 MHz. Japan's quasi-zenith satellite system, QZSS, is operated by the Japan Aerospace Exploration Agency, JAXA, and was first launched in 2010. While the other constellations have provided global coverage, QZSS maintains Asia-Oceania regional coverage between Japan and Australia. As a regional constellation, QZSS only has 4 satellites currently in orbit, with a plan for an additional 3 satellites in the few years. QZSS signals transmit at the same frequency as GPS L1, 1575.42 MHz, L2, 1227.60 MHz, L5, 1176.45 MHz, as well as L6, 1278.75 MHz. Another major regional constellation is the Indian Regional Navigation Satellite System, IRNS, operated by the Indian Space Research Organisation, ISRO, out of India. IRNS is also known as NAVIC, Navigation with Indian Constellation, and includes 8 satellites in orbit. The constellation's coverage centers around India, reaching west to include Saudi Arabia, north and east to include all of China, and as far south to include both Mozambique and Western Australia. NAVIC signals transmit on the GPS L5 frequency, 1176.45 MHz, as well as along the S-band, 2492.028 MHz. GNSS applications rely upon satellite signals to complete their task efficiently and accurately. These applications range across many different industries, from agriculture to automotive to defense, but generally will fall into 5 major categories. 1. Location, determining your position in the world. 2. Navigation, identifying the best route from one location to another. 3. Tracking, monitoring an object's movement in the world. 4. Mapping, creating maps of a specific area. 5. Timing, computing precise timing within billionths of a second. For example, farmers need consistent routes over their fields to optimize seeding, fertilizing, and harvesting. They rely on GNSS for their location and tracking of their equipment. In some cases, Farmers may use GNSS to map their fields before planning their routes. In the automotive space, vehicles use GNSS for location and navigation purposes. If the vehicle is autonomous, then tracking becomes even more important to continuously monitor potential hazards in the environment. GNSS is used in aerospace for location, navigation, tracking and timing. The United States Federal Aviation Administration uses timing information from GNSS satellites to synchronize hazardous weather reports across the country. Episode 7 of our Introduction to GNSS webinar series goes into further detail about how diverse applications use GNSS. There is a range of GNSS equipment that has been developed to support different applications across a variety of environments. At its most basic, to use GNSS you require an antenna and a receiver. Antennas act like a gatekeeper to satellite signals by accepting high-quality signals and rejecting low-quality ones. A range of antennas have been developed to best support different applications, including compact antennas, fixed reference antennas and high-performance low-size and weight antennas. Receivers are available as OEM receiver boards for users to install into their existing solution, or within an GNSS enclosure ready to be used. Receivers do the work of demodulating the satellite signal and computing the user's position, navigation, or timing measurements. Because users require both an antenna and a receiver, Hexagon Novatel developed smart antennas that already combine the two technologies into an all-in-one solution. Depending on the application's need for precision, signal resilience, and reliability, there are additional technologies that enhance the performance of GNSS receivers. These additional technologies are often included within receiver enclosures, like Novatel's GNSS and inertial span technology. Inertial navigation systems, INS, and their inertial measurement units, IMUS, integrate heading, velocity, attitude and heave motion measurements with GNSS measurements for a more complete and three-dimensional understanding of your position. If users are operating in environments where there may be attempts to jam GNSS signals, or falsify position, navigation, and timing coordinates, also called spoofing, they may invest in anti-jam solutions. Novatel's GPS anti-jam technology, GAJT, helps protect users' antennas from being jammed or spoofed so they can continue receiving GNSS satellite signals to their receivers, like what we see in this case study from the British Army's Light Dragoons. In some cases, firmware like Novatel's GNSS Resilience and Integrity Technology, GRIT, can be added onto GNSS receivers to build a more resilient and robust positioning system against jamming and spoofing attacks. Across all environments and all applications, users often rely upon GNSS correction services to augment their solution's accuracy and reliability. Correction services are available in either a real-time kinematic, RTK, method, or through precise point positioning, PPP. These services help mitigate and resolve positioning errors from atmospheric and ionospheric activity, multipath effects, orbital errors, satellite clock errors and more. The satellite-based augmentation systems, SBAS, mentioned earlier are one example of correction services, but there are many subscription-based services available that provide greater accuracy, availability, and reliability. Many technologies, algorithms, and innovations have been developed and refined to optimize GNSS satellites for position, navigation and timing. Many solutions rely upon a combination of the above technologies to use GNSS to their advantage. GNSS does far more than supporting Google Maps. In this blog post, we've highlighted the technologies, organizations, and real applications that support, innovate upon and use GNSS for position, navigation, and timing. With over 70 years of development, GNSS is at the core of our everyday lives. This sentiment will only become more true as GNSS-based autonomous applications like self-driving cars become more ubiquitous. GPS was the first GNSS constellation to be launched. The Russian GLONASS, European Galileo, and Chinese BeiDou constellations were launched later and are also operational. The benefit to end users of having access to multiple constellations is accuracy, redundancy, and availability. If one system fails, for any reason, GNSS receivers, if they are equipped to do so, can receive and use signals from satellites in other systems. System failure does not happen often, but it's nice to know that if it did, your receiver may still be able to operate. Regardless, the ability to access multiple constellations is of particular benefit where the line of sight to some of the satellites is obstructed, as is often the case in urban environments or areas with lots of trees. A satellite navigation or sat-nav system is a system that uses satellites to provide autonomous geopositioning. A satellite navigation system with global coverage is termed Global Navigation Satellite System, GNSS. As of 2023, 4 global systems are operational: the United States' Global Positioning System, GPS, Russia's Global Navigation Satellite System, GLONASS, China's BeiDou Navigation Satellite System, and the European Space Agency's Galileo. Regional navigation satellite systems in use are Japan's Quasi-Zenith Satellite System, QZSS, a GPS satellite-based augmentation system to enhance the accuracy of GPS, with satellite navigation independent of GPS scheduled for 2023, and the Indian Regional Navigation Satellite System, IRNS, or NAVIC, which is planned to be expanded to a global version in the long term. Satellite navigation allows satellite navigation devices to determine their location, longitude, latitude, and altitude/elevation, to high precision, within a few centimeters to meters, using time signals transmitted along a line of sight by radio from satellites. The system can be used for providing position, navigation, or for tracking the position of something fitted with a receiver, satellite tracking. The signals also allow the electronic receiver to calculate the current local time to a high precision, which allows time synchronization. These uses are collectively known as positioning, navigation and timing, PNT. Sat-nav systems operate independently of any telephonic or internet reception, though these technologies can enhance the usefulness of the positioning information generated. Global coverage for each system is generally achieved by a satellite constellation of 18 to 30 medium Earth orbit, MEO, satellites spread between several orbital planes. The actual systems vary, but all use orbital inclinations of 50° and orbital periods of roughly 12 hours, at an altitude of about 20,000 kilometers or 12,000 miles. Thank for watching this video.